Okay, so welcome back everyone. Today we're going to be talking about section 5.4, and there's two topics that we're going to be talking about in this section. Each one of these topics is a fairly small thing to cover. The first one we could talk about, that we'll talk about, is what's called the Net Change Theorem. So what does the Net Change Theorem say? It says the integral of a rate of change is a net change. So what is that telling us? Can we break this down? Well, it first mentions the integral, and then it mentions a rate of change. But remember, a rate of change is just a derivative. So the integral of this derivative, and it's across some time, so a to b, is what? The net change, or another way of writing net change is f of b minus f of a. But notice that that is really just the fundamental theorem of calculus. It's saying that part of it is just that the derivative and the integral are like inverses. They cancel each other out. Now, why are we restating it in this way? Well, it's important for word problems. So we can talk about some word problems here. So we'll do two examples. Our first example is if oil leaks from a tank at a rate of r to the t gallons per minute at time t, what does this integral represent? Well, from the net change theorem, we could say that it represents well, remember this is going to be gallons per minute, so that's a derivative. So it's going to represent the net change of gallons, that is oil leaked. Right, because if you take the integral of this, let's say the gallons leaked, we'll call this function g of t, so that g prime of t is r of t. Then this integral is really just g of 120 minus g of 0 by net change theorem. And g of 0 at time 0, you should have no leakage. So really, the net change of the oil leaked, or the oil leaked after 120, I'll assume this is seconds. So just remember, with all these problems, you're looking at the net change. Okay, so then there's a part 2 to this problem. Let's put in a specific function. Okay, let's suppose this is x plus 1 over x squared dx. let's evaluate this. Okay, so you could rewrite this, split up the fraction into x over x squared plus 1 over x squared dx, or 0 to 120, 1 over x plus 1 over x squared. This thing is going to be the natural log of the absolute value of x, and then plus what? Minus 1 over x. And you can check that, but basically all I'm doing there is this is x to the negative 2 power, x to the negative 1 power, and we know the integral of 1 over x is natural log of the absolute value, and you can just put this in your calculator and see what you get. And actually, just to be consistent, you technically can't do this integral, so we're going to change this in the time equals 1, just so that we have numbers that work out. So what do we get? Well, we'll get natural log of 120 minus 1 over 120, and then minus natural log of 1, or 0, minus 1. Or natural log of 120, which is some number, it's not a nice number, but it's a number, minus 121 over 120. And that gives us what exactly? Well, from what we said before, this gives us the gallons leaked. Okay, that's how these net change problems go. Okay, so let's do another example. Let's say I have velocity at time t is t squared minus 2t minus 3, and my t is ranging from 2 to 4. What is the displacement and the distance traveled? So let me just explain the difference between the two, because these are a little bit two terms that they sound very similar, but they're a little bit different. So let's assume I have something that starts right here, it travels over here, and then comes back until it gets really close to where it was before. Now the displacement is just the change in coordinates. So it's just this little bit. But the distance traveled is the length of this entire path that it took to get there. So those are two different things. How are we going to get one versus the other? Well, if we call it displacement, a lot of times they'll call that something like delta x. Well, that's just the integral and our bouncing from 2 to 4 of this function. So we can find this. An antiderivative of that is by the power rule, 2 cubed over 3 minus 2t squared over 2, which is just t squared, minus 3t evaluated from 2 to 4. And you can put that in your calculator, and what do you get? Well, you're going to get, so the first one So you'll get negative 20/3 for 4, and then minus, once you plug everything in and you combine like fractions, you'll get negative 22/3. So what are you left with? Well, the displacement, the delta x, in this case will be 2/3. And you can check my math just by evaluating that. Okay. So the displacement is 2/3. What about the distance traveled? How do we do that? I'll call that d for distance. It's still an integral, but now we have to take the absolute value of this thing. Now that's a little different from what we've done so far. Actually, let's call this capital D. Not to confuse it with the little thing at the end of the integral called the differential. Okay, so we could look at this function. When is that function positive and when is it negative? Because remember, absolute value of x is x when x is greater than or equal to 0 and is negative x when x is less than 0. So on this interval, when is that function positive and when is it negative? Well, t squared minus 2t minus 3 factors into t minus 3, t plus 1. So it has zeros of 3 and negative 1. And you can do the first derivative test, but it's a parabola, so it has a positive coefficient, meaning it will be an upwards parabola with a 0 here and a 0 over here. So it looks something like this. And so if negative 2 is over here, or if positive 2 is over here, positive 4 is over here, notice that it will be negative from 2 to 3 and positive from 3 to 4. Okay, so because you have that, you can actually split this up, right, into 2 to 3. We're going to do a similar split up as we did in one of the problems in the previous section. 2 to 4 of, well, I'm running out of space, so I'll write just the function name, f of t, or v of t. And then on this interval, it's a negative number. So it's going to be 2 to 3 of negative t squared minus 2t minus 3 dt. Plus, on 3 to 4, it lies above, it's positive, so the absolute value drops out. So what do we get? Well, this is going to be negative t cubed over 3 plus t squared minus 3t, evaluated from 2 to 3, plus the negative of it. Evaluated from 3 to 4. And we can calculate this, and what do we get? Well, it will be negative 3 cubed is going to be 27 divided by 3 is 9, plus 3 squared, which is 9 again, minus 3 times 3 is 9, and then you subtract, evaluating at 2, so negative 8/3, and then plus 4 minus 6. So those two are just from taking this function, plugging in 3 first, and then subtracting, plugging in 2. Okay, and then we have to add to that. Well, first we plug in 4. 4 cubed is going to be 64 divided by 3. And then minus, what? Minus 16 plus 12. And then you subtract, putting in 3 again. Negative 9 plus 9 minus 9. And you're going to get some value, some number. Or sorry, that will be the opposite of what we had before. Okay. And you can compute this. These two terms should cancel. And then you have whatever those other terms evaluate to. And that gives you what the distance is. Okay, so that was just the one aspect of this section. The other aspect is going to be something that you've actually seen before. We just never use this terminology for it, or this notation we're about to use. We're going to talk about what are known as indefinite integrals. Up to this point, we've talked about definite integrals, which was something like, say, from 0 to 5 of x to the 4th dx is a definite integral, and it's just some number. What we're going to talk about is something like this. Notice I didn't put any numbers here. And this is called an indefinite integral. Which is a fancy term for most general antiderivative. But we already know how to find those. So like, for example, on this one, if I told you to evaluate this indefinite integral, all I want is the most general antiderivative. You add 1 to the exponent, you divide, and then you add c. And that's it. That's all I'm asking where I'm asking for this thing. It looks like an integral, but I just didn't put the bounds of integration. I didn't put the little numbers on our elongated s. So, and that's all I'm asking for the indefinite integral. It's really just giving some notation to the idea that we had before of most general antiderivative. So let me just put up an example or two. Let's just do first one, x to the 1.3 plus 7x to the 2.5 dx. The indefinite integral would be x to the 2.3 divided by 2.3 plus 7 over 3.5 x to the 3.5 plus c. You will get the answer wrong if you don't have the plus c. Yeah, and so let's do another one. X squared plus 1 over 1 plus x squared dx. Well, the first one is power rule, x cubed over 3. This is just a constant, so it's antiderivative x. And the antiderivative of this thing, well, it's not one of our standard power rules, but it is a standard one we do know. It's arctan. Remember the inverse tangent function? And then we need plus c. Because the inverse derivative of the inverse tangent is 1 over 1 plus x squared. So that's it for indefinite integrals. So a quick note about indefinite integrals. Is, remember, it's the most general antiderivative, which is not a function because the c can be any number. It's actually a family of functions. So because c could be 0, but it could be 1.5, or it could be pi, or it could be negative 10, or anything you want. And it would still work as the antiderivative. So that's just this little caveat with what the indefinite integral is. It is a family of functions. And we just compute it by computing antiderivatives. Okay, so that's it for this section. We'll be continuing on next time with something called U sub, or the substitution rule, which is, in this class, what our major integration technique is going to be. I will see you all online for that next time.